Hi everyone. So today we're going to continue on our discussion on function of a single variable. So first thing is just a quick reminder. Remember that whenever we have a function, let's say we're given a function f that map from R to Rm. So remember that this function represent a curve, or sometimes referred to as a path in Rm. And the reason why that does that because we actually use it as a parametric. Actually, maybe I'll write it this way. And f is in parametric representation. So therefore implies the following. When you define the function f, this is how we actually would define the function f. So f map from R to Rm would actually be f of t equal to some vector x. So in this scenario right here, our t is our parameter. And as a matter of fact, you can think of t as the time variable. Then what is vector x? Vector x in this case would be the position vector in Rm. So what does that mean is the following. If I were to draw the graph of this function f, so imagine, for example, let's say function f map from R to R2. Then in this case, f basically represents a curve on the xy plane, since that's what R2 is. So meaning we could kind of draw the graph of that and just to see how that look like. So here's my xy plane. And then you could have the curve that looks something like this. And here would be our f of t equal to vector x, which in this case would be xy, which is what we call vector x in this case. So now, therefore, let's say at a specific point on this graph, it doesn't matter where it is, but let's say right here, at this point, I would say at t equal to t sub 0, the position on this curve is given by f of t sub 0. So t become kind of like a time variable, and then you can think of the function would give out the position at any given time. And then when you kind of trace all the position that you got, you will kind of now have a curve. Now, as you probably remember from BC calculus, whenever you define a parametric curve, it's important to define the direction of the curve. So in this case, I can say that this curve probably go like this. Okay? Because the curve, because defined parametrically, it doesn't always go from left to right, because that's the left to right is just the positive x direction. But t can go in any direction because t is not shown on the graph. All right? So now come the next big question. What does the derivative represent? So we call from BC calculus let's say given a function f of x, or maybe y equal to f of x. The derivative of this function f prime of x define two things. Define either number one, the slope of the tangent. That's from a geometrical standpoint. or 2 is referred to as instantaneous rate of change. So it's either defined as the slope of the tangent or instantaneous rate of change. So now the question comes down to what happens if I now have a different type of function. So notice that from BC calculus, the function that you learn is function f that went from R to R. So now for us, when we talk about function f that went from R to Rm, what happens if I found the derivative of this? What would that represent? So this is basically what it represents. So let's say given f that went from R to Rm. So first thing I notice is the following. If f prime, okay, well, maybe I'll write this way. Let's say given the function f that went from R to Rm, and let's say this function is f of t. If f prime of t exists, okay, and let's say if I devalue f prime of t as some value exists and it is non-zero, well, technically speaking, a non-zero vector, because f prime in this case will have to be a vector. And maybe I'll write this up here. So if f map from R to Rm, and let's say the function is f of t, then its derivatives f prime is also attribute map from R to Rm. So therefore the derivative is also a vector. So if f prime exists, and if I plug in a value t sub 0, and its value exists, and is also give out a vector that's non-zero vector, then this vector is called one of two things. So we're going to define the first thing first. It's called the standard tangent vector for f of t at t sub 0. So this is defined to be what we call standard tangent vector. Now, is that a surprise it's called that we use the word tangent to describe this thing? Well, it's probably not, because I already told you that the derivative you learned in last year in BC calculus also talk about tangent. So here, this talk about tangent should not be a surprise to you. But here's the important part, is this word right here. Is the word standard. Okay, why is it called a standard? Because of the following. Any multiple of f prime of t sub 0 will be going in the same direction or opposite direction of f prime of t sub 0. So therefore, technically speaking, any multiple of f prime would also kind of go in the same direction and therefore become a tangent vector. So, however, they are not the standard tangent vector. So they are called just tangent vector. So there's a difference between standard tangent vector versus tangent vector. Standard tangent vector is what f prime of t sub 0 would be, while tangent vector are any multiple of that. So there's a slight difference between the two. So how do we actually form this f prime? Well, simple. Remember, we already talked about it. So when you have a vector value function like this one, which map into Rm, we can define the function using coordinate function. So if f of t is equal to, let's say, f1 of t, f2 of t, to f sub m of t, then the standard tangent vector is basically this: f prime of t, which is equal to f1 prime of t, f2 prime of t, dot 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 to f sub m prime of t. So that defines what we call standard tangent vector, which basically just take the derivative of each of the coordinate function. Now, what does the standard tangent vector do? So imagine that you have some kind of curve. Okay, so let's say we have this curve right here. Let's say this is the curve f of t, where f in this case map from r to some unknown dimension rm. Okay, so now what happened is, let's say at this one point right here, which is at t equal to t sub 0. The important part is the position at this point. The position is at this point is given by f of t sub 0. Okay, remember we talked about it. The function f gives you the position vector at any given t value. So at t sub 0, the position will be given by f of t sub 0. So now then, what does the standard tangent vector do? The standard tangent vector defines the tangent direction at that point. So this is the standard tangent vector. And that standard tangent vector will be given by f prime at t sub 0. And that is the reason why this f prime of t 0 cannot be 0, because if 0 then would not define a standard direction to go. So therefore it does not have a standard tangent vector. What's special about the standard tangent vector is that if you somehow leave the curve at this one point and no longer travel along the curve, then you'll be going in the tangent direction. Literally, the expression flying off the tangent. That's basically what it means. And of course, it makes sense that when you have a tangent vector, but not the tangent vector, you basically just have the same exact direction vector, but it just probably shorter length, a longer length. Okay. Now I'll explain to you the special, why standard tangent vector is so special, but we'll get to that in a little bit. So the next thing I do want to talk to you about is the following. Now that we have a standard tangent vector and a position, notice the following. Notice that f of t sub 0 is a position vector because it defines a position in space, which is on this curve. And the standard tangent vector defines a direction of that you would go. Therefore, it's a direction vector. So now think, if I have a tangent vector, that's a direction vector, and a position vector, what can I form? Well, I can form this. So what we're going to try to do is the following, is to write the tangent line to a curve. So let's say given a curve in Rm, let it be represented by the function f that maps from R to Rm. We can now write the tangent line of this curve at a specific given t sub 0 value. The tangent line for f of t at a specific t sub 0 value is given by the following formula. So remember, in order to write a line, what I need would be two things, a direction vector and a position vector. So we're going to now define that the direction vector is basically going to be our standard tangent vector, but technically speaking, it could be any tangent vector. But I am going to write down standard tangent vector because that's the vector, the direction vector that I want you to use. But technically speaking, you could use any tangent vector. So standard tangent vector at t sub 0, which basically would be the expression f prime at t sub 0. Notice that is a vector in Rm. Now I also need a position vector to define where the line is. So that we will use the point of tangency, which is where we write our tangent. And a point of tangency at t sub 0 will be given by f of t sub 0. Because remember, the function f gives out position, and f prime gives out the tangent direction. So therefore, notice that I have direction vector and position vector to write this tangent line, and this tangent line very likely not only in R2 but also in higher dimension also. And based on what we learned in chapter 1, we can only write a line in parametric representation in dimension higher than 2. So therefore, in this case, very likely that, as a matter of fact, it's almost guaranteed that this formula here is actually going to give us a parametric representation of the tangent line. So the parametric representation of the tangent line for f of t at t sub 0 is, so here we depend on how you want to write the equation, the parametric representation. You can definitely write something like this: vector x equal to t times f prime at t sub 0 plus f at t sub 0. So notice that in this case right here, if you probably think about it, you probably recognize that this look like this formula. And you're correct, because it's exactly the same formula, except that the u is a specific vector u, which is f prime of t sub 0, and vector v is a specific vector, which is f of t sub 0. In your textbook, it also gives this notation, which they call the tangent line, lowercase letter t, because we use lowercase letter to usually represent lines, and then uppercase letter to represent plane. And to indicate that this is a line in vector form, go say t, vector t of t is equal to t f of f prime of t sub 0 plus f of t sub 0. Now, I don't like to use this notation as much because of the vector t, which kind of get confusing with the parameter t. But here, the vector t here basically represent tangent line. Okay, so I would actually going to ask you or prefer that you use this formula right here. But I want to show you this because that's what the textbook use. So just so that you know. All right, so maybe we'll do a very simple example just to illustrate, okay, the concept here. So let's say we have this problem right here. Let's see. Let f of t equal to, let's say, cosine t sine t for 0 to 2 pi. And I'm not going to be equal to 2 pi because, once again, 2 pi is the same as 0. Okay? Let's see if we can do the following. A. How about let's find the tangent line at t equal to pi over 4. So, should be relatively straightforward. All you really have to do is to figure out f prime of t and f of t, and then just plug into the formula. The formula is right there on top, right there. All right, so let's go for it. So f of t is equal to cosine t sine t, so f of pi over 4 would equal cosine of pi over 4 sine of pi over 4. And so that, if you remember your trig values, cosine of pi over 4 sine of pi over 4, they're exactly the same. They're both radical 2 over 2. And now all I need is to do a derivative of it. So I'm going to go and find f prime of t. So remember, to do f prime of t, all you have to do is take the derivative of the two coordinate function, which in this case, cosine t and sine t. So derivative of cosine t is negative sine t. The derivative of sine t is cosine t. So now I'm ready to go ahead and plug it in. So f prime f pi over 4 would actually equal to negative ret 2 over 2. Ret 2 over 2. So now I'm ready to put my tangent line together. My tangent line will be equal to t multiplied by the direction vector, which is f prime, plus the position vector, which is given by f. All right. Now, I'll give you another one to try out. So you can definitely try this one out. How about I ask you to find the tangent line at t equal to pi over 2. So I will ask you to pause the video and just go ahead and do the problem on your own, and then unpause the video to see the answers. So f of pi over 2 would just be cosine of pi over 2 sine of pi over 2, which come out to be 0, 1. And we'll have f prime of t, so I'm going to just plug it in. F prime of pi over 2 will be negative sine of pi over 2 cosine of pi over 2. So that come out to be negative 1, 0. So therefore, combine them together, vector x would equal to, actually, it doesn't matter, I can write here. Vector x would equal to t times negative 1, 0 plus 0, 1. Now, some of you might recognize actually what's happening here, because some of you probably recognize the equation f of t equal to cosine t sine t. And yes, you should, as a matter of fact. As a matter of fact, you definitely should recognize the equation f of t equal to cosine t sine t, because you learned it in BC calculus. And that is the equation of a circle. So therefore, if you think about it, this function f of t actually represents the curves, which is a circle, on the xy plane. So let's go and look that up. Let's see, we're going to draw a picture of this. So here's xy plane, and here's my unit circle. Right, pretty good. So this is my f of t. Oop, actually, I'm going to probably put it over here instead. And notice that, remember, because of parametric curve, probably a good idea to kind of indicate the direction. Oh, okay. Nope, I don't want to do that. All right, yeah, I'm going to leave it. Okay, so that's my circle. So notice the circle actually go counterclockwise. That's how we define the circle. And this one is a unit circle. So therefore, this would be 1, this would be 1, this would be negative 1, this would be negative 1. So now if you think about what happened to the two tangent lines that we formed, notice that when t equal to pi over 4, it basically just means that we rotate a quarter of a, well, actually 1/8 of a circle. So therefore, our first tangent line will actually be in this point, which is ret 2 over 2. Oops. Ret 2 over 2. And the direction, negative ret 2 over 2, ret 2 over 2 actually will be this direction. This is the direction, negative ret 2 over 2, ret 2 over 2. And so the tangent line will actually be this line right here. So here's our tangent line at pi over 4. Good. Now, if you think about it, then what happened to the other tangent line? Well, the other tangent line is here. At pi over 2, we're at this point, 0, 1. And our tangent line is this, tangent direction, our standard tangent vector is this one. Negative 1, 0, which is completely horizontal, which makes sense because it's right at the top of the circle. And so our second tangent line would be this one. This is our second tangent line at pi over 2. And notice that both of these kind of fall into the expectation that we think it should do. Well, it makes sense because, I mean, remember math has to be internally consistent. So it's consistent to the geometry aspect of it that we think it should happen. All right, so now I'll show you next thing. So next concept that I want to talk to you about is this. So remember I told you that I will talk to you about why the standard tangent vector is so important, because of following. So standard tangent vector, we interpret it more or less like using geometry in a geometrical sense. We try to draw the tangent line to a curve. So that's what the derivative actually represents, the tangent direction. But from a physical standpoint, imagine that you are not looking at the curve, but rather looking at an object moving along that curve. Then the derivative actually take on a very different meaning. So just like the derivative you learned last year, which could be the slope of the tangent, but it can also be instantaneous rate of change. Here we go try to interpret it using more physics. We're going to talk about velocity and acceleration. So if f of t represent not a curve, but rather represent an object moving along a path or a curve, then f prime of t is actually called the velocity vector. And because of that, it defines the direction of movement of this object. Okay? So therefore, it's kind of like what you learned in BC calculus about velocity being the derivative. Here is exactly the same thing. The only difference is that last year, when you learned about velocity, it had just a scalar, and with the positive and negative to indicate forward or backward direction. But now we have something more powerful, because now we have a vector, which allows us to actually define any specific direction that we want. Now, just like last year, when you have a velocity, you can also define something very similar but not quite the same, speed. We will define the speed to be the length of the velocity vector. So therefore, the magnitude of the velocity vector become what we call the speed. Therefore, we go define this to be v of t, and that is the length of f prime of t. And as a matter of fact, I probably should write this right here. We'll go add that in. It defines the direction of movement. Velocity vector is called vector v of t. Notice that different than v of t, where v here has no arrow on top, indicates a scalar. So therefore, we can think of v of t is just equal to the length of vector v of t. Oops. So here's what vector v of t is. This is what v of t is. Okay. Important to know the distinction between the two. But before I do that, let's talk about acceleration also. So what do you think is acceleration? Well, simple. Acceleration will be the derivative of the velocity. So we will define the acceleration vector to be the derivative of the velocity vector, or the second derivative of the function f of t. And the acceleration vector is basically vector a of t. which is equal to either, think of it as v vector v prime of t or f double prime of t. So therefore, if you remember learning it last year in BC Calculus, unfortunately we probably, I'm going to have to wrap this up so we can probably talk more about it tomorrow's video, which hopefully will be the last video here. So just let me finish this part. So if you recall from last year, when you learned a topic called rectilinear motion or motion along a line, we learned to describe a motion through the following three types of functions: position function, velocity function, acceleration function. Now we are learning a little bit better because we now talk about things that are not just along a line, but are rather in on R2 space or higher. Then now we can use vectors to talk about. So therefore, the first thing we have will be the position vector. So therefore, we're describing a movement by using these three things. The position vector will be vector x of t, which is usually referred to as just f of t. That's the position vector. And in this case, f map from r to rm. So therefore, our position vector is actually defined a position in rm. Velocity vector. So velocity vector is vector v of t. That would equal to f prime of t. And notice that f prime of t also map from r to rm. So therefore, define a direction in rm and with a single input t. Now this one is a tricky one. How about speed? Speed is v of t, which is equal to length of f prime of t. And v, in this case, map from r to r, is the only unique one out of the bunch because it's a real number, it's a single variable function that's also real value, as you expect because speed is just a number. There's no direction or anything, it's the magnitude. And then we have the last thing we're going to talk about is the acceleration vector. Vector a of t. That's equal to f double prime of t. And f double prime of t is still map from r to rm. So collectively, these describe motion in rm. Now, unfortunately, my time right now is already 32 minutes in, so I guess we'll finish up this whole thing and the remaining concept that I want to show you in 4.1 in tomorrow's video. All right, talk to you later. Bye-bye.